Imagine this for a second. There are something of like 100 million invisible monsters just drifting through our galaxy.
Silent wanderers.
Exactly. We're talking about stellar mass black holes, the leftovers from dead stars. You can't see them because they don't eat anything, they don't emit any light. They were basically just ghost stories.
Until now, maybe. Today we're doing a deep dive on a proposal that, well, it pretty much hands us a flashlight.
Or a hunting license. This is a proposal to MAST, that's the Mikulski Archive for space telescopes. And the idea is to build what they're calling seed catalogs.
Think of it like a massive most wanted list. It's an infrastructure project designed to help us finally spot these things.
And the mission here is to take decades of, dusty old data and mash it up with the brand new Nancy Grace Roman Space Telescope.
All to weigh the dark parts of the galaxy. And to do that, you have to use a trick called gravitational microlensing.
Right. The idea that a black hole passes in front of a star and its gravity acts like a lens, making the star's light flare up.
Yeah. And since these black holes are, totally dark, lensing is basically the only way we have to find them. But there's a catch. There's always a catch.
There always is.
Ground-based telescopes like the OGLE experiment, they can see the flare. They can measure how long it lasts. The problem is that data is, well, it's mathematically degenerate.
Which is just a fancy way of saying it's ambiguous.
Exactly. You don't know if you're looking at a heavy black hole that's really far away
or a much smaller, dimmer star that just happens to be a lot closer. You get two different answers and no way to know which is real.
Right. To break that tie, to get the actual mass, you need to measure something called the Einstein radius. You have to see the tiny shift in the light's position.
Something ground telescopes just can't do. They're too blurry.
You need space, which is where this seed catalog idea comes in. This is more than a list. It's a 3-tier treasure map posted at MAST.
And it's designed to stack the deck before Roman even gets off the ground.
It is. So Tier 1 is all the history. It pulls data from OGLE, which has been watching like 2 billion stars for years. It flags all the long-timescale events.
The ones that last for hundreds of days, which is a huge hint you're looking at something massive.
A real smoking gun.
Yeah.
Then Tier 2 cross-matches that with data from the Gaia mission.
Okay, so that's the context layer. Gaia tells us how things are moving, the parallax. So you know where these potential black holes are and where they're going.
And Tier 3 maps all of that directly onto Roman's future field of view.
And we have to talk about Roman. Launching late 2026, this thing is an absolute beast. Its main instrument has a field of view 100 times bigger than Hubble's.
And it sees in near infrared, so it just punches right through all that galactic dust that hides the good stuff. But the real issue is speed.
Okay.
To see why these catalogs are so vital, just look at the classic case. OGLE 2011 BLG 0462. This is the first definitive isolated black hole we ever found, about 7 solar masses.
But pinning that down was a nightmare. It took, 6 years of Hubble data? And a huge reanalysis that wasn't really settled until 2025.
6 years for one object. We can't do that if we want a census. We need to find thousands, millions of them.
So the seed catalogs let Roman know exactly where to point its high-res eye the second it comes online.
We go from finding one lucky needle in a galactic haystack to, population-level science.
And what's really cool about this, with all the data Roman is going to produce, is where the idea came from.
Yeah, that's a great part of the story.
The proposal actually credits Bart and Brad, 2 members of the public community, as part of the motivation.
Which is a necessary shift, I think. It's about democratizing the science. By putting these science-ready tables out there at MAST, you're opening the door for students, for citizen scientists, for anyone, really.
We're going to need all hands on deck to sift through this data.
Absolutely. So we're not just finding black holes. We're actually testing the fundamental rules of how stars live and die.
Right. And that gets to the real end game here, doesn't it? The mass cap.
This is it. We know neutron stars max out around, 2.1 solar masses. And the black holes we typically see start around 5 solar masses.
But what's in between? Does anything even exist in that forbidden zone?
Are there impossible stars hiding in that gap?
That's the billion-dollar question. And this whole project is designed to finally answer it.
The answer is probably already sitting on some old OGLE hard drive. It's just waiting for Roman to give us the final clue.
A wild thought to leave you with, that the missing link in stellar evolution might already be in an archive, just waiting to be discovered. Thanks for diving in with us.